Kumar Singh, the teaching assistant for the course Experimental Physics 2. So this is the sixth live session for this course, and today we will continue our discussion of prisms, and I will recap some more concepts related to prism, and we will see some examples based on them. And yeah, so let's start. Today I want to derive uh, the formula for hello. Hello, Mr. Divakar, can you hear me? Hello, good morning. So yeah, hello. So I was just starting. So today, so I'm going to derive the formula for angle of deviation for a thin prism. Okay, so let's start. So can you see the screen properly? Okay. So suppose this is your prism. This is the angle A, B, C. Okay, and suppose a beam of light is coming like this. Okay, let's call it B. Then it will deviate inside from this normal. Okay, so this is the original path, but due to the prism, the ray deviate like this, and then again here this will be the normal, and it will deviate away from the normal because here the air has a low refractive index than the prism. Okay, so and this is, let's say this point is S. This angle is angle of emergence E. This is angle of incidence I. Okay. This is normal N. This normal is K. And let's call this point O. This is the first reflecting angle R1. This is the second reflecting angle R2. And let's call this O and this one R, this point. So, sorry, Q. Let's call this Q. This one is O. And so the angle of deviation is, so this is the final path. So let's extrapolate it backwards. So this is the angle of deviation, delta. Okay, and this point is D. So angle KTS is your angle of deviation. Okay, I'll write out all the angles. angle NQP is your angle of incidence, angle RQO is R1, angle QRO is R2, angle KRS is angle of emergence. Okay, that's all the angles we have, and obviously angle QAR is your A, angle of prism. Okay, so we want to calculate the formula for angle of deviation in terms of refractive index and angle of the prism. Okay, now so one thing is, as you can see here, angle TQR, okay, angle TQR is simply I minus R1, right? Because this is I and this whole is also I, opposite angles. So this small angle TQR is just I minus R1, this angle. Okay, and angle TRQ, this angle is E minus R. Is it okay? Yeah. Then you know the exterior angle property of a triangle, right? So this angle of deviation delta will be equal to, you don't know? Okay, yeah. So this delta will be what? Angle TQR plus angle TRQ, right? This angle, because this is an exterior angle of this TQR triangle, so it will be equal to these both angles. Fine. And so this is this and this. So I minus R1 plus E minus R2, right? We can write it like this, minus R plus R. Fine. Now in triangle QRO, so this is the QRO, this triangle, QRO, we have R1 plus R2 plus angle ROQ equal to 180 degree, right? Angle, all the angles of a triangle. And one more thing we have is angle AQO is equal to 90 degree, because NO is a normal on this side AB, so AQ is 90 degree, and similarly angle ARO is also 90 degree, the normal on this AC side, because normal. Okay, any doubt till now? Okay, so then we have sum of these angles, angle ARO and angle AQO is 180 degree. Okay, but in the quadrilateral AQOR, we have two other triangles. We have two other angles, angle A and angle ROQ. Now you know that all the angles of a quadrilateral are is equal to 360 degree, and these two angles are 180 degrees. So these other two angles will also be 180 degree, sum of them, right? So now you see, uh, from this equation and this equation, you have R1 plus R2 equal to A, right? Because they both are 180 degree, and so this and this get cancelled, and just R1 and R2 equal to A remains. Okay, and then uh, from here you see delta is I plus E minus R1 R2 is since A, so it's now these two formula are very important. It will come up in solving many problems. Okay. Now, but we need to find the formula for angle of deviation in terms of refractive index. So to incorporate the refractive index into our derivation, we'll use the Snell's law at the AB interface. Okay. So from Snell's law, we have mu equal to sine I by sine R1, right? And we'll assume that these angles are small, so sine I will be I and R1 will be R. Okay. Because for small angles, sine theta is equal to theta almost. Okay. So then you have I equal to mu R1, and similarly on the other side, so this is for Snell's law at AB, and at AC you have mu equal to sine R2 by sorry not R2, sine E by sine R2. and here also taking small angles, it will be E by R2. So you have E equal to mu R2. Now we have the formula for I and E. We can substitute that here in this third equation. Okay, so let's start from here. So in third equation we can write delta equal to, so I is what, mu R1, and E is what, mu R2 minus A. So you can take the mu outside, then it's just R1 R2 minus A, and we have this result where R1 and R2 is equal to A. So mu A minus A, which you can write as A outside, taking A outside, mu minus 1. Okay, so the final formula is delta equal to mu minus 1 A. So this is the result that I wanted to derive, and this is true for a thin prism because we have assumed that all the angles are small. So this is valid for thin prism. Thin prism means this angle A is of the order of 10 degree at most. Okay, so this is a very important formula and it will be used in many problems that I'm going to solve. And the formula for uh, dispersive power of a prism, right? Do you know dispersive power of prism? This I discussed in my last lecture also. So dispersive power of a prism is simply uh, how well it can disperse the different frequency or wavelength of light uh, which are going through it. So you know that when we shine a white light on a prism, it disperses the white light into uh, mm, many different into all the 7 colors of a rainbow, right? And the dispersive power is simply uh, we can say how well it can resolute the different wavelength of light. So and the way it will do is that if it can separate the red and violet light properly, then we will say that it has a good dispersive power. So the formula for dispersive power is uh, angle of deviation for violet light minus angle of deviation for red light divided by the mean deviation. Okay, so this formula will also be used. Okay, so that's all. I think these formulas are enough for today. So let me go to the first problem. Have you any doubt here? Want to ask anything? Mr. Divakar, is everything all right here? Okay, thank you. Okay then. So the first problem that we have here, uh, the critical angle between an equilateral prism and air is 45 degree. So here we have a equilateral triangle. Equilateral triangle means all the three sides are equal and three angles are equal. So if the angle of incidence in the first refractive surface is 45 degree, then angle of incidence in second refracting surface is. So what's given is the oh, sorry. What's given is the critical angle, okay, uh, between the prism and air, which is 45 degree. Okay. So from this information, what can we find? Can you tell me? What can we find from critical angle information? Okay. So you know that when a light is incident on a surface, okay, and if it the angle of refraction is 90 degree, if it goes like this, just grazing on the surface, then we call this incident angle as critical angle. And if the angle of incidence increases from this, like this, then the light will be reflected, which is called a total internal reflection. So you can use the Snell's law here. So suppose it has a refractive index mu. So sine theta c. Uh, so suppose here you have a air which has a refractive index 1 will equal to mu of sine 90 degree. Okay. So and sine 90 is 1. So your theta c will be just sine inverse. Do you know about this formula? Yeah. Okay. So here theta c is given 45 degree, and we can calculate the refractive index. So just sine 45 degree equal to mu. So mu will be 1 by root 2. Okay. Now No, and also in the problem, it's given that the angle of incidence on the first refracting surface is 45 degree. So we can calculate the angle of refraction. So suppose the beam goes like this. Okay, so we can calculate the angle of refraction here using again the Snell's law. So sine 45 degree equal to mu sine R1. Sine 45 degree is again 1 by root 2 and mu is 1 by root 2 sine R1. So R1 is so sine R1 is 1, so R1 is 90 degree. Okay. Okay, something looks strange here. Yeah, because the critical angle is 45 degree and this incident angle is also 45 degrees. So obviously the refracting angle is the 90 degree, like here, correct? Then what is asked is the angle of incident in second refracting surface. Okay, so and you know the just now I showed you the relation that R1 plus R2 equal to A, right? And you know that for equilateral triangle all the angles are 60 degree, right? So this angle A is 60 degree. So here you can calculate R2, uh, which is, wait, it's coming negative. I think there is some mistake somewhere. Hmm. Oh, okay. So actually, this this statement, the way it is written, the critical angle between an equilateral prism and air is 45 degree. Okay, so that means is uh, what it means is that not not the critical. So you have to think it opposite way. Okay, so this is the prism and this is the air in this case. So this mu will be on the other side. So basically, this prism has a rarer medium. This prism is rarer medium than air, so its refractive index is lower than the air. Okay, so then it will be 1 by mu and sine 45. So mu will be under root 2. You understood? I've applied this formula in the opposite way. Okay, so this will be the refractive index. So let's put it here. Then sin R1 will be 1 by 1 by 2, and R1 will be 30 degree. Yeah. So then R2 will be 60 minus 30. No, sorry. R1 is 30. A is uh, A is 60. So R2 will be 30. Right? Yeah. Now it's correct. So then uh, we have R2 and 30 degrees. So this C option is correct, right? Because incidence is through this angle, uh, through this side, we have to find. So this form. We don't need to apply Snell's law on this surface because we already have this formula which relates the two refracting angle and the angle of prism. Fine. Yeah, so sorry for the confusion here. If here it would have been written like between an air and prism, then this derivation that I did earlier was true. But since it's written that between an equilateral prism and air, so we have to assume that the angle of incidence is on the prism side. Okay, so that's why we have to use this. Okay, so then uh, let's move to the second problem. Here, the question is the dispersive power of prism depends upon. So just now I showed you the dispersive power formula, which was angle of deviation for violet minus angle of deviation for red and the mean deviation. Okay. So which of the following options you think is correct? Does it depends on the shape, or material, or angle of the prism, or height of the prism? What do you think? Any guess? Yeah. Hello. It depends on the refractive index, right? So, so that means material. Yeah, correct. So yeah, that's right, because I also gave you this formula that angle of deviation is mu minus 1 a. So we can write this dispersive power formula in terms of refractive index. And the refractive index is a property of material, right? So that means that depends on the property of material of the prism. But in this formula, the angle of the prism is also here, right? So shouldn't this both option should be true? What do you think? So let's put this in this formula. So mu v minus 1. So instead of del v, we can write mu v minus 1. Angle of prism is same. Then minus del r is mu r minus 1 a divided by, yeah, a is constant. Here we'll have mu mean minus 1 by a. So a will cancel, right? So just it only depends on the mean. So that's why this option is not true. Yes, it was a trivial question. Okay, next problem. The refractive angle of a prism is 60 degree, and refractive index for a given color of light is under root 2. So for minimum deviation, the angle of incidence will be. So for minimum, the condition for minimum deviation, do you know what that is? Any idea? Yeah, thank you. So we have this formula R1 plus R2 equal to A, right? And for minimum deviation, this will be just 2R equal to A. So R equal to A by 2, which is 30 degree, right? And then we need to find the angle of incidence. So we have R, so we can use this Snell's law because we have given the refractive index. So mu sine I by sine R, okay, sine I equal to mu under root 2 into sine 30 degree, and so sine 30 is 1 by 2, so sine I is 1 by root 2, so angle of incidence is 45. It was also easy problem. Just you have to know this condition that for minimum deviation, this all the angles are equal, I1, I2, and R1. Okay, so moving on to the next problem. Now this one is little it's not a tough problem, but little calculative. So the problem is critical angle of a glass with respect to air is theta 1, okay, and of water with respect to air is theta 2, and then the critical angle for water in glass surface is theta c. Then you have to find whether of these conditions satisfy, which one is true, okay. Now the only thing that is given here is the refractive index of glass and refractive index of water, and we know that the refractive index of air is 1. So suppose this is the normal, suppose this is air, this is glass. So uh, this critical angle of glass with respect to air means this is the this is the incident beam, and this will be the theta 1, okay, and here it will be going like this 90 degree, the refractive angle, and we can apply Snell's law here. So mu g sine theta 1 equal to, so this is air, refractive index is 1, sine 90, so 1 by mu g equal to sine theta 1, and mu g is given 3 by 2, so sine theta 1 equal to 2 by 3, okay. Now similarly for water and air, so this is water, this is air, this is theta 2. Here also so calculating the same way, we'll find that sine theta 2 is just the opposite of mu of water, which is 3 by 4, right? Now we can do the same thing for glass and water. So here we have glass, here we have water. This is the theta c, mu g sine theta c equal to mu w. Sine 90 is just 1, so sine theta c is mu water is given 4 by 3, and mu g is 3 by 2, so it will get divided here, so it will be 2 by 3, and we will get 8 by 9, right? Now you have sine theta 1, sine theta 2, sine theta c. Now based on these values, can you tell me which one is greater? So you have sine theta 1 is 2 by 3, sine theta 2 is 3 by 4, and sine theta c is 8 by 9. Now in out of these three, which one is greater? Obviously this one is greatest, and then out of these two we have this and this, and since sine theta uh, uh, for a, so suppose it's a increasing function, increasing and continuous function, so the behavior that we have for sine theta will be same as for theta, right? So we can say that theta 1 is less than theta 2 and less than theta c. Correct? Okay. This one is also simple problem. Then one problem of lengths, just to remind a simple concept. So we have two lenses, and the focal length is given. If one is 15 centimeter, f2 is 30 centimeter, and they are held in contact like this, suppose, and the image of an object at infinity will be formed by the combination at. So you know that if the object is at infinity, the light rays will be parallel, right? And for parallel beam of light, uh, image will be formed at the focal point, right? Because it will all be converged on the focal. So we have to just find the focal length of this combination of lens, right? And from the lens maker formula we can derive this formula. So effective focal length of this combination is just equal to sum of these two. Oh, sorry, this is minus 30 negative. Okay. Uh, you know how to derive this formula? Should I remind? So you know this lens maker formula, right? Mu minus 1 by r1 plus 1 by r2. You know this? Yeah, so from here you can derive this formula basically. Uh, because you know the focal length, uh, focal lengths are f1 and f2, suppose, and this refractive index is assumed to be the same. So both the lens are made up of the same object, then this will be same. And this radius of curvature, it is also assumed to be the same. So the combination will be just addition of 1 by f. It's a simple derivation. You can do it quickly. So from in this formula we can just put both values like this, and we'll get 1 by 30, right? So effective focal length will be 30 centimeter, and this is the, I mean, you can use the thin lens formula to calculate the, but you know that the object is at infinity, so this is 0. So the image is formed as at the focal length. simple problem of ray optics. Okay, then sixth problem. So here we have a green light refracted. Sorry, a green. Okay, sorry. A green light refracted through a prism produces minimum deviation if I1 and I2 are angle of incidence and angle of emergence in this situation. Then, oh, this one is very simple. You already answered this, that both should be equal, right? So this one simple. Okay, then we have here one problem, that the angle of prism is 60 degree. So this is not a thin prism, so that uh, this formula that I derived will not be applicable here. Okay, so angle of prism is 60 degree, and the angle of deviation, minimum deviation, is 30 degree. So then the angle of incidences and angle of emergence are respectively. So we are asked I and angle of emergence. No, but uh, we cannot use this formula, but we have a different result, that I1 plus, sorry, I plus E minus A. This formula is always valid, right? Because if you will see, while I was deriving this, so this formula came at here, right? And after that I assumed for small angles these conditions. So this formula is always valid, correct? So this I can use here. And yeah, In equals, so 2I minus A, and we know the delta in A, so I will be simply 45 degree. Correct. So yeah, you see how important this formula is. This formula is very important. Then next question. The angle of prism is 60 degree. So A equal to 60 degree, and refractive index is under root of 7 by 3. The maximum angle of incidence in the first surface for which the emergence of the ray through the second surface is possible is. Okay, so this problem is little involved. So you don't have a thin prism, and you're asked that the maximum angle of incidence, okay, I, for which the emergence, so the emergence is possible only when the R2 is less than or equal to critical angle, right? Otherwise it will get totally internally reflected. So for maximum, let's take R2 equal to theta c, correct? And then we can apply Snell's law on the second refractive surface. So you know that mu of prism is given, so mu sine R2 equal to, so this is the image. So you have incident beam, it's going like this, okay, this is your R2, and this is the emergence, which is angle of emergence is 90 degree, okay. If this angle is greater than R2, then the light will be get totally internally reflected. So R2 is theta c, and here we have, so this is air, refractive index is 1, and sine 90 degree, which is also 1. So sine R2 is simply 1 by mu, that is 3 by 7 under, right? And also we have this result, R1 plus R2 is equal to A. So then we can calculate R1, this R1, which is A minus R2, which is uh, okay, let's keep it like this, A minus R2, and then we can apply Snell's law on the first surface, this surface. So air sine I is equal to prism sine R1, so sine I equal to 7 by 3. So sine R1 we can write A minus R2 using this result, and so you have sine I equal to under root 7 by 3, and we can use the sine A minus B formula, which is sine A cos B minus cos A sine B, right? And you can find the cos R2. So cos R2 is just 1 minus sine square R2, right? So 1 minus 3 by 7, which is 2 by 7 under root, correct? And then A, we know that it's 60 degree, so let's put all the things here. So sine 60 degrees 3 by 2, cos R2 2 by root 7 minus cos 60 1 by 2, and sine R2 is 3 by 7 under root. So here this 7 cancel this 7, and what remains, or better, this 2 to cancel, 3 cancel, 3 here cancel, so 1 minus half, right? Just half. So I is 30, right? Okay, so then next problem, ninth problem. This is our second last problem. Here the problem is the angle of a prism is 30 degree, again not a thin prism, and the refractive index is under root 3. A ray makes incident in one of the refractive surface normally and get refracted from the second surface. The angle of deviation of the ray. So what's happening is this is the normal, and the ray of light is also incident through the normal. And this is the normal on second surface, and here it's getting deviated like this. So now you can see that the angle of deviation is same as the angle of emergence, right? Because you have no deviation here on the first surface. So whatever the deviation is through the angle of emergence, correct? So uh, this is sorry. So this is 30 degree, this is 90 degree, so this will be 60 degree, right? And this is 60 degree, then this is also 30 degree, because this hole is 90 degree, right? So we can apply the Snell's law here. So we, yeah, oh, uh, you mean I2? Wait. So sine I2. Let me check. Okay. So sine 30 is 1 by 2 root 3 by 2. So I2 is 60 degree, right? Yeah. So this is the angle of deviation. Something is not looking right. Is this okay? The calculation? Yeah. Okay. Yeah, maybe it's. Mm, yeah. Yeah, it's correct. Okay. Then let's move to last problem. Here we have a refractive index of the material of prism is given, which is under root 2. The angle of incidence at minimum deviation is 45 degree. The angle of the prism and angle of minimum deviation is asked. And this one is simple problem. So first let's calculate the first refractive uh, angle by applying the Snell's law. So here sine 45 degree equal to mu sine r, sine 45 degree 1 by root 2 is 2 sine r. R is 30 degree. Yeah. Now for minimum deviation, I1 equal to I2 equal to, and R1 equal to R2 equal to R, and we have this condition 2i minus a, and we have 2r equal to a. So just because so then r is a is simply 60 degree, and Indian time is 2 into 45 minus 60, so 90 minus 60, 30 degree, right? So which option is correct? This one, D. Yeah, so these were fairly simple problems, and I hope you have no doubt in anything. So, Mr. Divakar, can you tell me about yourself? So, what are you doing? Huh? Yeah. Oh, you are a professor? Where? And which subject? Okay. Where? No, I mean university. Which university? Which one? I didn't hear. Oh, okay, okay. So, is this course helping you? Okay, fine. Yeah, that's good. So what do you teach mostly? Hmm. Okay, okay, great. Yeah, I mean, you can think of some experiment using prisms also, right? Yeah. Okay. Thank you for joining. See you next Saturday.